Today we're looking at chapter 15, and so I will pull the video up. All right, so chapter 15 is on geologic structures. When we talk about these, what we're referring to is the fact that you have these tectonic plates on the surface of the earth, and heat energy from inside the earth forces them to move. So the plates come together, they slide past each other, they move apart. These different motions actually will deform or reshape the surface of the earth. So the stresses that we're talking about fall into three broad categories. You can have compressive stress, and you'll notice in the drawing that the blue arrows representing the forces point in the same direction towards the center of the object. So you would find this if you had tectonic plates that were at converging boundaries, where they came together. The second one is for tensional stress, and you'll notice the blue arrows point in opposite directions. So maybe tectonic boundaries that are moving away from each other, diverging boundaries. And then we have the third one, which is shear, and the forces are offset from each other. And so you might find this at transform boundaries. So all of them will act to change the shape of the rocks. So let's look at the drawing for just, the graphic for just a second. The top three illustrations are for rocks that are deformed close to the surface, so at shallow depths. The bottom three are for rocks that are deformed much deeper underground. So if you push the two rocks together in compression, because faults almost never occur directly up and down, they're almost never vertical, they're almost always at an angle. So if we push them together, you'll see that in this drawing, the one on the left is going to slide up and the one on the right is going to slide down because we pushed them together. In tension, where you're pulling them apart, you can see again, the faults are not straight up and down, but at angles. So the block in the middle will actually slide down because the ones on either side are moving away from it. And then shear will cause offsets and in the crustal blocks in the rocks, because the rocks are sliding past each other. And again, there'll be, notice there are breaks, there are gaps in the rock right here and on this end. Suppose we look at it depth. So in compression at depth, you'll notice that the rocks are folded. We get arching up and sinking down. You'll notice that tension thins out the rocks in the middle and may even make a slight depression, a slight bowl shape. And then finally, when you have shear, the rocks are not cracked because under pressure they're pliable, they're ductile. And so they distort, but they don't crack and shift. All right, moving along. So rocks will change because of stress in three different ways. You can have plastic strain, and in that the rock is bent or molded, but does not return to its original shape after you release the stress. So after you quit tugging on it and pushing it, it'll stay in the new configuration. Elastic strain occurs when the rock is deformed, but when you stop exerting a stress on it, it's going to rebound or recover to its original shape. And then finally, fracturing, the rock will actually break under stress. Most of the time, this tectonic movement takes place along faults, so cracks in the bedrock. It's almost always a very slow motion, but if you've got an earthquake, it's very rapid. So when we look at rocks, we study them oftentimes to learn something about the geologic past. Sedimentary rocks start out in horizontal layers, and tectonic forces push and pull them, and change them. Excuse me. Your geologic map is going to show different kinds of rock units, so different kinds of rock, different ages of rock. It'll show folds and faults and even ore deposits. You can find mines locations on these sorts of maps. We draw them based on aerial views of the region, but it also requires usually a physical survey of the area. Someone has to go in and verify the types of rock that are located, and then they're drawn. The computer and satellite imagery has enhanced this process and made it just amazing. So outcrops are rocks that are visible at the surface, and we do look at those to make the maps. This is a section of a geologic map for the state of California. It's from the Sacramento region, and it shows the Midland Fault. So you can see the Midland Fault is labeled on this. The different colors correspond to different kinds of rock, and each kind of rock is a different age. So the symbols that are in the rock, like this QPC, or the Q or the E or what KU, all of those would be identified on a legend that would give you the color and the symbol and tell you what kind of rock it was, the name of the formation. These are shorthand for the name of the formation. And that would give you information about the rock. The pale blue is probably water. It almost always is on maps. The lines indicate faults, so places where you would expect movement. And these funny little symbols, this sort of skinny long line with a short line coming off at a 90-degree angle, is a strike and dip symbol, and it shows you which way the rocks are tilted. So speaking of strike and dip symbols, we need to define those. So the orientation of your rock layers is defined by the strike and the dip, and that is called the attitude. Defined by the strike and the dip, and those two together make up the attitude of the rock. So you could have horizontal rock layers, you could have vertical rock layers, you could have tilting layers. They're almost always tilted. So the strike is the compass direction formed with the intersection of a rock layer with the horizontal. The angle of dip is just how much is it tilted? Is it tilted down a little or a lot? So if we look at this diagram, the brown and then this sort of gray color represent rock layers. This blue represents imaginary water. So here we have our tilted layers. The imaginary water hits the tilted layers right along this line. That's the strike. It's where would the horizon hit the rock. So water will make our imaginary horizon. That's the strike. And then the dip direction just tells you which way did the rock layers dip down. Remember, they start out horizontal. So they're going horizontal. And in this case, they went then down into the left in our drawing. So let's look at some of the strike and dip symbols that you'll need to know for probably a quiz. So horizontal layers are indicated on a map with a circle and a plus sign in it. So if your geologic cross section looks like this, where you've got 3 different kinds of rock, the geologic map represents the top layer. It's the ground you walk on, and it's usually colored appropriately. And then the symbol would be this circle with the plus sign filling it, because these are horizontal layers. If you have vertical layers, it's a long skinny line and a short cross piece. Depending on how it's tilted, some people think it looks like a cross, some people think it looks like a plus sign, whatever. So here are cross section with the vertical layers. And here is the strike and dip symbol. The long line always goes parallel to the existing layers. And the short line, I like to describe it as telling you which way would the water run if that were the only rock layer there. So if we only had the white rock and it rained, water would go off both sides of it. And so the little cross piece, the direction of dip points both ways. Dipping layers are, again, a long line with a short piece in the middle of it. So if we have our layers like this, 3 different layers, and you can see that this black layer is tilting down and to the right. And so here is the strike, always parallel to the existing rock layers. Here is the dip pointing in the direction the rock layers went. I like to tell people that if you stood on the surface and you drilled straight down, that's the side of the strikes where you would hit the same kind of rock you've got all the way down. So for example, on the left side, well, let's try the black rock. If at the black rock, we drill down and look on the left side, you can see we don't hit black anymore, we hit right. But if we look on the right side and we come down, we hit black all the way down. Or another way to think of it is if the black layer is the only layer you've got and it rains, which way is the water going to roll? Well, it's going to roll downhill. It's kind of like a slide, so to the right. Maybe I'll do a video about this. Okay, overturned layers. So they go all the way to vertical and then flip over and turn even more than that. So it's sort of like a candy cane with a cross piece. We'll look at some of our folds. They're bends in the rock. They take on different shapes. They're a result of large-scale compressions applied at depth. If you look back at that first drawing in the information, we talked about at how at depth you get things that arch up and sink down. Those are folds. So you always have a central axis and then limbs that bend. So let's look at an anticline. An anticline, again, the rock layers start out horizontal, so 1, 2, and 3. 1 is the oldest, 3 is the youngest. Oldest on the bottom, youngest on the top. If we push it together and it arches up, push it together, it arches up, it would look like this. If we let erosion take place down to this level, and that whole top layer gets eroded away, you'll be left with distinct bands. To draw in the geologic map, you need to watch the separate video on anticlines. It includes a clay model of the anticline and shows you how we get the actual shape. So you need to watch that because you need to be able to draw the geologic map for an anticline. Now, what does an anticline look like? Well, again, the rocks arch up. So this is what it looks like. The rocks are arching up. Let's go the other direction and look at a syncline. For a syncline, again, we start out with layers 1, 2, and 3, old on the bottom, young on the top. It sinks down. You push in from each side and now it looks kind of like a gutter or a taco, if you will. So it sinks down. If we erode away, we still have 3 different kinds of rock visible. To draw the map, you need to look at the separate video on synclines because you will be expected to know how to draw the geologic map for a syncline. And the rock layers come down. You can see in this photograph, the rock layers come down. Domes are like synclines, but instead of the forces pushing in from each side, they push in all the way around in 360 degrees. And so you end up with a bowl-shaped configuration. Looks more like a series of 3 nested bowls. So here's rock layer 1 on the outside, 2 in the middle, 2 next to it, and then 3 in the very middle. And again, to draw the geologic map, you need to look at the video on basins. There's a separate video on basins. Here is a graphic showing you a section of geologic map from Michigan. Here is the Upper Peninsula, UP. if you're there. And here it shows you the Michigan Basin, and you can see it looks like nested circles. So hopefully when you watch the video on basins, you'll understand where those nested circles come from. Or maybe you can see it from the little graphic that if you slice off the top, if you start out with nested circles, you're going to end up with nested circles. And it's the ages. You'll have the oldest on the outside and the youngest in the middle. And that's how they knew this was a basin. They looked at the ages of the rocks. The rocks were older on the outside and the very youngest rock was in the middle. And this is just a smaller view of that to give you a bigger sense of what's going on. This is another basin. This one is in Algeria, so in Africa. This is from Google Earth, as you can see. And I love that from a Google Earth perspective. Let's see, we're at 800, oh, I'm sorry. We are at almost 30 miles above the surface of the Earth. I think I read that right. And you can see the shape, the nested rings of rock. And again, the way they would know it was a basin was by looking at the ages. Basins have old rock on the outside and the very youngest in the middle. And this is just another view of the same thing. This is from a website called Zoom Earth, and it gives you just a different perspective on it. But again, I liked it because you could see I think you can see the rock layers a little clearer on this one. So domes go the other way. Instead of a nested bowl shape, it's a nested dome shape. So again, you push in all the way around, but you push it in so it looks like we've turned those bowls upside down. You will have, with this one, because you're pushing in all the way around, the young rock 3 ends up being on the outside, and the old rock 1 ends up being trapped in the middle. And so we should expect to see nested circles with 1 in the middle and 3 on the outside. And there is a video to show you where this comes from. So you'll want to go back to the chapter assignment and be sure you watch the video on domes. Here's again a photograph. This is of the Sinclair Dome in Wyoming. You can see it. And this is from Google Earth. Here's the Sinclair Dome again. And again, the way we know it's a dome, oldest rock is in the middle, youngest on the outside edges. And this is from Zoom Earth, just another view of the same thing. All right, plunging folds. So folds are caused by compressive forces. And if the rock layers stay horizontal and then are compressed from the sides, but the base is still resting, as it were, you're going to have the folds we've talked about, the anticlines, synclines, domes, and basins. But suppose your rock layer then gets tilted. The bottom comes up and the top goes down. It gets somehow non-horizontal. When that happens, we have what's called a plunging fold. And there is a video on plunging folds, and you're best just to watch that, and then we'll talk about some drawings that show it. So if a fold is plunging, that you can have a plunging anticline or a plunging syncline. And the way we know what type of fold it is based on the sequence of the ages of the rocks. So anticlines have the oldest rock in the middle of the formation. Synclines have the youngest rock in the middle. So we look at where is the oldest rock. This is a photo of a plunging fold. I know there are people down there, kind of like that. I know you can't tell from the photo whether it's a plunging fold or is it just a dome or a basin that was drowned or an anticline or a syncline. I know you can't tell. Geologists have looked at the rocks that are under the water and the surrounding area in order to tell you it's a plunging fold. And here's another view. And again, I realize from the photograph you can't tell. So let's look at some other types of folds. Open folds are folds where the rock has not been deformed very much, so it's sort of a gentle up and down. Here's a photograph of an open fold. It goes up and down just a little bit. And again, you need to be able to recognize these drawings, or if I ask you to even draw it, you ought to be able to draw an open fold, or if I draw one for you, tell me what it is. An isoclinal fold or a hairpin fold, and again, you need to be able to draw it. They're formed by intense compressive stress. So you start out with that open fold and you smush, 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 and the rocks come together and the fold gets tighter, tighter, tighter. I've always thought this looked like that ribbon candy you can buy at Christmas time. So the folds are very tight in an isoclinal or hairpin fold. And here is a photograph of one. You can see how we come up and down and up and down, and it's a tight fold. And then we have overturn folds. So with overturn folds, what happens is that the forces at the top are not the same as the forces at the bottom. Instead of the loop staying straight up and down, it tilts. You can see in this particular drawing, the forces at the top are stronger, so it's going to tilt to the right. And here is a photograph of an overturned fold, and I don't know if that's a ruler or looks like a ruler. A lot of times they put rock hammers down or car keys to give you perspective, but that looks like a ruler. I don't know. And then finally, recumbent folds. So they have been, if you take your overturned fold and you keep pushing, this base is going to slide under the top fold, and you'll end up with something that's drawn like a backwards S, and that's a recumbent fold. That's a recumbent fold. And you can see in the photograph that it's on its side. And as I said earlier, it starts out, a fold will start out progressive. So you might have an open fold and then you compress a little more and it becomes an upright. And here we've got an overturned fold. And then finally we push a little more and it's a recumbent fold. So it can be progressive. So fractures and faults, we want to talk a little about them. So you've got a crack. If it shows no movement, we call it a joint. If it shows movement, it's called a fault. So the fault line, again, the break is almost never straight up and down. It's almost always at an angle. The part of the rock that is associated with the wide base is the footwall. The part of the rock that's associated with the overhang is called the hanging wall block. So wide foot is a footwall block, wide overhang is a hanging wall block. And so we break faults up into 4 basic categories. You start out with a dip slip fault. So in a dip slip fault, we have our 3 layers of rock, 1 on the bottom and then 2 in the middle and 3 on top. And here's our fault line. And all we've done is let the block on the right slide down and the block on the left go up. And so, and then we've said, okay, erosion comes along and evens off everything that sticks up. So the block on the left loses its whole top layer down to about the middle of its second layer. And what you would see then, the ground you would walk on the left side, it would be all this darker colored rock, which is rock layer number 2, which is older. So the line down the middle separating our geologic map into 2 parts is the fault line. It represents this line where the 2 rock layers came together. So rock layer 2 on the left and 1 on the right, because we erode down to this shaded layer on the left and we stay at layer number 3 on the right. Oh, I'm sorry, that says 1. That's supposed to say a 3. I don't know where my brain was with that. Let's fix it. Rock layer number 3. And so what we have then is the block on the left went up. That's why we wrote a U for up, and the one on the right came down. That's why there's a D for down. So up on the left. Normally you wouldn't put it in these shaded little boxes, the unshaded boxes, but because the left side is shaded, I wanted to make sure you could read it. And so here's our geologic map. If I gave you this rock configuration, you ought to be able to draw the geologic map. And this is a photograph of a dip slip fault. You can see here's a dark layer, here's a dark layer, light layer, and sort of spotted on the top. And again, you'll see that the one on the right looks like it came up, the one on the left came down with regard to each other, in relationship to each other. It could be that one of them sat still and the other did all the moving, but we refer to up and down with respect to each other. All right, a strike slip fault. This one's a little more complicated. So motion's in the horizontal direction only. So here's our 2 blocks. This is the fault line right here. Here's our fault line. And you'll see instead of up and down, they go in and out. So the block on the left side, which is the footwall block, comes out of the page towards us. And the one on the right, which is the hanging wall block, goes into the page away from us. So here is our fault line. Because there's an empty spot on the right-hand side, the rock moved on the right-hand side away from us, there's a line there. And because there's an empty spot on the back side, on the left-hand side, there's an empty spot there. So rock layer 3 is on top. It's the ground we walk on. On the rock on the left, it comes all the way to the front edge. So all the way to the front edge. Here is the void in the back. Here is the void. It gets filled in over time by younger rock. So more sediment comes in and fills it in. So we had 3 on the top, and this is younger than that. It's rock layer 4. The arrow indicates that the rock on the left comes out of the page towards us. The arrow on the right indicates that the rock goes into the page away from us. There's a void on the front edge, the edge closest to you, for the block on the right, and it gets filled with young rock number 4. This is a strike slip fault in lab. We'll talk more about those. But we talk about them as being right lateral or left lateral. So if you are standing right here, then this is a left lateral fault because this rock band looks like it's moved to your left. If you flipped and you were on the other side and looking at it, it would still be a left lateral fault because this band of rock would look like it had moved to your left. All right, oblique slip faults. These have got everything put together. They go up and down and in and out. So the block on the left is coming out of the page towards us and going up. The block on the right is going into the page away from us and sliding down. So if we erode away the part that sticks up, that would be the top layer on the left-hand block. Then on the left-hand block, we're left with layer number 2. Did it again. I've got my numbers backwards. I'm so sorry. That is a 1. This is a 3. I'm apologizing. This is terrible. At least we caught it. Okay, I guess I was worried about the shading. Anyhow, 1 on the bottom, 3 on the top, old on the bottom, young on the top. So left-hand side, we wrote off the light-colored rock. We have the dark left behind. We said it went up, so we get a U. We said it came out towards us, so the arrow comes towards us. The one on the right, the arrow goes away. The one on the right, we're left with layer number 3. And the one on the right we said went down. There's a D for down. Rock layer, there's a void up here, an empty spot, and there would be an empty spot back over on the left side, just like on the strike slip faults, and they get filled with younger rock layer number 4. Normal and reverse faults. Normal faults, the hanging wall moves down. Reverse faults, it moves up. Sometimes you'll see this mentioned. We won't overdo it. And that gets us to thrust faults. So with a thrust fault, the fault line, which is right here for our drawing, the fault line is at a not quite horizontal, but almost angle. So that would be completely horizontal. This is just a little horizontal. It tilts just a hair. And what that does is if the block on the left is being pushed, if these two blocks in the drawing are being pushed together, if the little break in them is gentle enough, one is going to slide, let's see, the break is gentle enough, the one on the left is going to slide on top of the one on the right. And that gives you an interesting pattern. It gives you young rock on top of older rock on top of, whoa, now we're back to young rock, older, and then oldest. So as you drill down, you get this alternating pattern. You get young and old, young again, then old again, and then the oldest down below. And that tells you it's a thrust fault. Again, a very gentle break and this funny young, old, can't make up your mind pattern. And I know without knowing the ages of the rock, this wouldn't really mean anything to you, but you can see here's the fault line. And you can see these layers writing over these layers. Now we have a section on the fold diagrams, and we will talk about that in lab. We'll talk about that in lab.